Okay, so this presentation covers what it means. First of all, kind of gives a quick introduction to containers to people that are not acquainted with this technology, and basically offers a proposal of what is required to use containers with RDMA. After we present the introduction, we'll go into the various components that are required. So what are containers? So containers is a server virtualization technology whose purpose is to run multiple instances of user space applications. Now, each one of these instances has the same look and feel as running on a full-blown dedicated server. It cannot distinguish, it cannot know the difference in principle. Now, when you talk about what an application is not necessarily a single process or thread. It could be many, many processes that comprise an application. And when you think about what you need to do to make applications isolated, applications, I mean, they don't work in the kernel. As long as whatever you answer to their system calls look like an independent server, then they're fine. They don't know the difference. So basically, this is what containers does and what distinguishes containers from virtual machines. So if you look at the figures, on the left-hand side, we have the now standard virtual machines. We have hypervisors, and we have this virtual machine. And basically, what the hypervisor does, it provides the illusion of a complete virtual server to the virtual machine, right? This virtual server has CPUs, it has a chipset, it has a keyboard, it has a monitor maybe, it has network cards. It's a full-blown server. And what you run inside your virtual machine is a full-blown software stack, where software means everything, right? From the pre-boot PXE down to the operating system loader, to the kernel, to the user space apps. I mean, it's a complete software image that thinks that it's running over real hardware, but it isn't. While containers, they don't try to virtualize virtual machines. The only thing that they want to do is virtualize the system calls. So at least in the Linux world or Unix, so think about the POSIX API that is virtualized rather than the physical machine. And because of that, if you look at the software that's packaged within a container, it doesn't contain any operating system code or any boot code or any driver code. The only thing it contains is application binaries, maybe data files, mounts, and libraries. That's about it. And also look at which entity provides the virtualization. So in the virtual machine world, you have hypervisors that do them, type 0, type 1, doesn't matter. On the containers, it's the operating system that does this virtualization. So these applications or containers are basically, they're just standard processes. I mean, they run just as efficient as any other process, okay? So the question is, what really makes up a container compared to any other process? So I'll just say what makes the difference is isolation, and we'll see it in a moment. Now, to give you like a more concrete example of what containers are, let's look at one very common example, Docker, which is basically a platform that allows you to very easily build, ship, and run applications based on Linux containers. And the main promises of Docker are as follows. First of all, it has a really simple packaging that is layered. And this means that you can create some base image, and then, which is, I think they use UnionFS or something. You create some files, some portion, some files. You can package that, and then you can take this and add another layer of files, and you can repackage that. And they have this huge repository of already set up applications where you can just take an image that, for example, is a Red Hat 6.5 user space with some versions of GCC and some versions of libraries. And you can take that Red Hat 6.5 and run it on SLES 11. It doesn't matter. As long, because the kernel APIs don't change that much. And what really distinguishes a Red Hat from SUSE is the libraries and versions. So you can really stack these images when you create Docker images. So just as an example, let's say that we wanted to make an image for HPC. Then we can have some base image that includes, like, I don't know, Red Hat 6.5 because I know I need that Red Hat and not the most recent one. OFS 2.4, some version of OpenAPI, some version of Lustre, and then that's my base image. Now I can give that image to my scientists, and then each scientist on his own laptop, they can use Docker, run this image, and then they can just install, like yum, install or update another version of GCC, some of their mathematical libraries, and their application code, and then post that image to Docker. And once they do that in your cluster, you can run basically a bunch of jobs, each one with its own libraries, its own tool chains, its own user space dependencies, its own libraries, and you can run everything on the same time and even different images on the same server, and they'll just run. The only caveat here is because this is containers, they're all sharing the same kernel. So if you need like specific kernel features, you're stuck. And of course, there are ways to override that with combinations of virtual machines and containers. I mean, use a virtual machine for the proper kernel version, and then run containers for differences in user space dependencies on top of that specific kernel. So Docker allows you for very easy packaging, and then you can deploy it on any server, on your laptop, in your laboratory. And when you start up services or when you start up applications, it's basically just starting up a process. So you set up an application within milliseconds instead of booting up a virtual machine. And this is why Docker is so awesome and it's gaining traction like fire. It's an amazing technology because it provides what application writers really need, which is just get my application running with the bare minimum overheads and the bare minimum provisioning to get that working. That's why it's so awesome. So when you come to Linux community, say, okay, tell me about Linux containers. And the first thing to understand is that there is no such thing as Linux containers. And the reason is containers is like a fancy name for just a bunch of Linux isolation mechanisms that are broadly partitioned into two. The first is namespaces, which are, again, there are a lot of types of those. You can have process ID namespaces, network namespaces, IPC, mount point and file systems, host names, user IDs. And what it means is that if I have a process that runs in an isolated namespace, let's say an isolated process ID namespace, if you do PS-A, you would see only a single process with PID 1. If you do fork, you'll see 1 and 2. I mean, where all those bash scripts and stuff that the Linux started with, the init scripts and all those daemons and stuff, it doesn't see them. It sees a virtual process ID namespace. Now, in terms of networking, you can do the same thing. So basically, Linux adds a tag for all the network constructs, meaning namely network interfaces, the routing tables, and net filter rules. So if you have your own network namespace, you can have your own IP addresses, your own net filter rules, and only the interfaces you decided to assign. And the same goes for other things. And the neat thing about this is it's a completely mix and match thing. So I can have like a so-called container that has its own mount points and file systems and process IDs, but it's still sharing the global host network namespace, for example. This would work great if you have a bunch of applications, each one listening on a different TCP port, but you still want to, isolate their CPU utilization. It will not work so well if you want to run 2 Apache servers, each one of them that needs to listen on port 80 and bind to IP address any. You can only have one of those, but if you have multiple network namespaces, you can have as many as you like. So I can run 2 Apache instances, plain Apache instances on the same server with different IP addresses, and they're both listening to IP address any. Okay, so this covers the namespace part. Let's look at C groups. So C groups is all about making sure that one application doesn't steal all the resources from other applications. So basically, it's a set of limits, but it's a very granular set of limits. The way that this subsystem is built is that you have a tree of nodes, and you can put process IDs in any of the leaves or in the intermediate nodes, and any constraint that you put in some point in this topology applies to all the subtree. So I can define, for example, let's say I have this 30% CPU constraint. It's shared by these 10 processes, but from these 10 processes, 3 processes are further restricted to 5% CPU. So you can do all this very powerful stuff, a very granular control about which resources and which limits each process gets. And another nice thing about C groups is whenever a process forks, the child, I think it inherits exactly the same limits as its parent. So if you have an application that starts as an emulated SUSE init script that runs your daemon that spawns, 20 processes that constitute your application, they still share the same limits as if they were running on a physical server, and you don't need to configure anything. There's no using script CI, track process IDs and put limits and dynamically move limits from one to another. No such thing. It happens automatically. So as with namespaces, C groups also have a lot of controllers. You can control block I/O, the number of I/O transactions. You can control CPU time. You control what CPUs are allowed to be used by some application. You can decide which device special files are visible to which processes, memory utilization, packet classification, packet priorities, etc. Okay, so this is not a full list, just like a sample of what you can do. Now, all these are mechanisms. Let's look a little bit about common practices for networking. So I'm starting with standard IP networking. So basically, the networking for containers is exactly the same as the networking for virtual machines. The building blocks are the same, apart that you have namespaces, but essentially you have, virtual bridges, bridge OVS, NAT stuff, net filter stuff. You have MAC VLAN, VLAN, and VETH devices. And using these building blocks, you can do any model that you want. Here's a short list of common models. So there are models where all the containers run in the host network namespace, as an example of where you have applications that listen on different ports. You can assign different physical interfaces. In this case, I treat VLANs and MAC VLANs as a physical interface because the switching between these interfaces either occurs in the external network or in the MAC VLAN device, but usually in the external network. And in this case, the container has a global IP. You can do standard bridging using a Linux bridge or OVS. You can do pods, which is what Google Compute Engine does. Mainly, a pod is a group of applications that share the same network's namespace. In this case, you have a global IP for the whole pod rather than for specific applications. You can do NAT, and you can do tunneling. And the figure on the right-hand side shows like trivial configuration for a bridged network, where you have on your host, you have your ETH0, and it's enslaved to bridge 0. And then you use this VTH concept, which is, VTH is a cute concept. It's a wire. It's like socket pair, but the endpoints are not sockets, but they're two natives connected by a wire. That's VTH. So you put one VTH in your host namespace, which is the orange rectangle. And then the other side of your VTH, you put in your specialized container-specific network namespace. And that's it. Now, anything that that container sends is going to get bridged by that bridge, and then, I mean, probably get flooded or sent out, etc. And here in this example, so I have here the same subnet mask. So I have here, I mean, they're both connected to the same physical ETH0, no VLANs. And we have here, each of these containers has a unique global IP. Global, I mean visible to the network. So one is 10.far02 and one is 03. So they're both in the same subnet, but they have different IPs. And this is the exact scenario of running two Apache servers, right? Each of those green boxes can listen on port 80, no problem. They have different IP addresses, exactly as if you had two physical servers that have different IP addresses and listen on port 80. Okay? So when we look at RDMA, how can we adopt RDMA to this kind of environment? So we want to, first of all, maintain simplicity and efficiency. So we just, we can share the same RDMA device. I mean, it's a kernel device, and containers are user space, so there's no problem sharing hardware. I mean, this is what operating systems are for. And we leverage the existing isolation infrastructure of namespaces and groups. And the other thing we want to do, we want to focus on application APIs, means verbs and RDMA CM, and currently exclude UMAD, UCM, all sorts of stuff that applications don't need to worry about. And also kernel ULPs, which usually, I mean, they can reside in host namespace, and they're controlled by BlockI or other means anyhow. So let's make a couple of observations. So first of all, isolating the verbs resources is not important. I mean, QP numbers are not well known. We have well-known service IDs. We don't have well-known QP numbers. Not only that, but applications can't even choose the QP numbers. So there's no reason whatsoever to do that. But RDMA CM does map very nicely to namespaces, because an RDMA ID is kind of an equivalent of a socket, right? You bind it to an IP address, you connect it to an IP address, etc. If I kind of look what needs to be done, I want to be able to associate QPs and address channels with a namespace, at least when they're called, to do proper ROCKY resolution. I want to associate RDMA ID namespaces so I can later on match incoming requests with the proper namespace. And I want to have isolated service IDs per namespace. Exactly so I can do an RDMA Apache server that opens TCP 80 mapped into the service ID port space. And I want to do it twice on two different containers. That's my goal. So when do we do these namespace associations? So QPs and address channels, they don't need to be associated during their whole lifetime. Basically, whenever I process a system call, I just look at the namespace of the calling process and then do the proper resolution within that context. Regarding RDMA IDs, I do need to save those because RDMA IDs could be bound to IP address sending. Then when a packet comes in, I want to make sure that it's accepted only by interfaces that reside within the same namespace in which that RDMA ID was created. So it does have to be associated with a namespace. So how does that resolution work? It looks like this. I have an incoming MAD coming from the fabric. First I ask, is this MAD an IPCM MAD? And again, this is by IBTA spec. If it's not, then all this namespace stuff is IP related. I have nothing to do. I just assign to the host namespace and I'm done. If it is an IPCM service ID, I do this lookup namespace procedure, which is divided into two. Either I already have communication IDs, in which case, I know that this packet belongs to a specific RDMA ID, which is associated with a namespace. So I have nothing much to do other than just take that RDMA ID's namespace and I'm done. The other option is that it's an unsolicited MAD, which means it's the first time I'm seeing this incoming connection. And in that case, I need to match it to an interface to learn about the proper namespace. Because remember, it's the interfaces that are assigned to the namespaces, where the interface determines the namespace. So when I have an incoming MAD, I need to match it to an interface. So now this depends on whether you're talking about InfiniBand or Ethernet. If it's InfiniBand, you need to match the tuple device, port, P key, and IP. That tuple uniquely defines an IP over IP interface. If you're working on Rocky, then device, port, VLAN, and IP, you could add MAC, but you don't have to. For any reasonable network, device, port, VLAN, and P key uniquely identifies an IP interface in Ethernet. And then you find the matching interface, and then you take the namespace from there, and you're done. And after you have your namespace, you can do the proper service ID match according to the proper namespace. Let's talk a little bit about controllers. So, as we saw, controllers basically govern resource utilization depending on the controller type. And when I try to extrapolate what we need to do for RDMA, I can think of the following kind of limitations. First of all, I want to limit the number of HCA contexts that an application can open. Usually, at least in our drivers, whenever you open HCA, you get the new doorbell page. We have quite a few of those, but it's still a finite resource. So if an application opens 2,000 doorbell pages, it's the device going to run out. There's nothing left, not for other applications, not for the kernel, and everything is deprived of functionality. The second is actual HCA resources like CQs, PDs, QPs, whatever. Again, we have a lot, but it's still a finite resource. And finally, you might do more advanced stuff like, I want to allow this application only to use service levels 0 and 1, because I have knowledge of the topologies that I'm using in my cluster, and I know that SL2 and 3 are mapped to a higher VL, and this is a non-privileged container. So I want to restrict the way that address handles are created and QPs are modified to ensure that the quality of service is not compromised. So we've done a lot of introduction. Let's look at how all of this comes together. So in this setup, I have two HCAs, an InfiniBand HCA and a Rocky HCA. On the InfiniBand HCA, I created 3 IP over IP interfaces. The left two are associated with the same P key. That's hex 8001. And of course, they have different IP addresses, naturally. But they still reside on the same subnet, which is 10.2. Now I have another IP over IP interface, which is associated with another P key, this time hex 8002. And naturally, this is a different subnet, so it resides on IP 10.3. That's on the InfiniBand side. On the Ethernet side, I have 3 interfaces. I have the physical interface, the untagged interface, ETH0, and have 0.100 on VLAN 100 and on VLAN 101. And since these are untagged or default VLAN 100, VLAN 101, these are different subnets. So their IPs are 11.1, 10.4, and 10.5. Now, I can take any one of these interfaces and associate with a particular namespace of some container. So, for example, application A, which can consist of actually multiple applications, multiple processes. It has access to IB0 and 1. And for example, it can listen on an RDMA service ID that's basically TCP port space 2000. And it can listen on IP address any, so it will receive any packet that comes from IB0 and IB1 and targets TCP port space 2000 is going to be accepted by that application. Now, in parallel, I can have another application, application B, that has interfaces IB2 and ETH 0.100, and it also listens on TCP port space 2000. But this application is only going to get incoming requests that either arrive at IB2 or on ETH 0.100. There's no problem with that. Okay? This is exactly what you would have expected if these two applications, A and B, would have run on physical servers. And then I have application C that has its ETH 0.101 interface, and it currently is not listening. It might connect in the future. And I also added here like a little bit of cgroup stuff. So let's say app A is limited by 10 QPs and 10 CQs, and app B by 50. And they can mix and match that with CPU utilization limits, basically whatever the Linux allows me to do. So where we are. So first of all, we have basically completed ServicelD namespace support for InfiniBand. You can use it today with any IP-over-IP interface and basically use containers with InfiniBand. The patches have been sent upstream, and we're waiting for Sean. Okay, I need to talk to Sean about it because we need to get some review of these patches. What's coming up? In addition to that, we want to add Rocky support, which is not a whole lot of work, especially the latest patch set that Emulex and Mellanox have submitted for generic Rocky address management. So this comes very naturally. Basically, what we did is now GID table entries reference net devices. Now, net devices are associated with namespaces. So adding Rocky support is a piece of cake. And RDMA controller groups, which I think Emulex has started seminal work on that. So if they submit the patches, then we're already well underway in that space as well. So this is coming really, really soon. So in conclusion, container technology is gaining a lot of traction for very good reasons. Now, it has its limitations, okay, because it has kernel dependencies. But at least those limitations don't apply for a broad range of applications. Where every application is dependent on user space applications, containers is a very interesting solution. Their efficiency makes them very attractive for high-performance applications, especially HPC clouds. And the reason is there's no virtualization, really. You're just running processes on a standard operating system, and you're just leveraging those container isolation tricks to run any application in any libraries. But in terms of performance, you're just interacting with your kernel. I mean, it doesn't get any better than that. So this is going to be good for HPC cloud, but it can also be good for even standalone HPCs. If you have, I don't know, a 20,000 node cluster, and you want to have people that have applications that use different toolchain, different GCC versions, and run on different operating system distros, you can give them that without any dual boot. You can still provision your whole cluster in a monolithic way. And I return here to this demonstration of layered packages. I come to my scientist and say, here's your base image, or you have two base images, one for SUSE and one for Red Hat. I validated it, I approved it, OFS is working well, MPI is working well. That's all you get. From there, you can add any layers you want. Add your own libraries, your own math, your own statistics, your own scripts, do whatever you want. You're guaranteed that this is going to work. As long as, of course, you don't try to replace libIB verbs or stuff that are part of the lower layers. But as long as the upper layers have nothing to do with our high-performance network, you're not going to break anything guaranteed. So RDMA containers, supports or provides basically support for these types of applications in a very secure and isolated manner. So I think, first of all, in terms of resource utilization, the infrastructure for C groups is so fine-grained, gives you so much control, you don't need anything more than that. And regarding RDMA CM, I think that as we evolve and make it, improve it, make it extremely better, I do expect that also HPC would start using it intensively. There's no reason not to. And we're going to work on that very hard in the next couple of months. So with that, I thank you. Yeah.
You want to say that you solved all the scalability issues associated with RDMA CM?
No. But I can tell you that it's on my top priority.
What?
Questions? One question?
One question.
Okay. Thank you.